For this presentation, we'll be taking a look at the performance analysis of Dijkstra's shortest path algorithm in serial and parallel execution. Our team members are Chris Sommer, Chase Kosek, Kevin Barnett, and yours truly, James Bryant. To introduce this topic, we took a look at a research paper that was written by Nadira Yasika, Nadia Alispahik, Arslanagic Elma, Kartovic Ivana, Lagumdirja Elma, and Novika Nosevic. And this research was conducted by the Department for Computing and Informatics and the faculty of the Electrical Engineering Department at the University of Sarajevo. This research was conducted in order to examine the parallelization capabilities of one of the most well-known shortest path graphing algorithms, Dijkstra's algorithm. So, looking at the applications of Dijkstra's, graphing algorithms are heavily studied in the field of computer science and information technology, with many well-known ones being breadth-first search, depth-first search, Dijkstra's algorithm, Floyd-Warshall algorithm, and several others. As for real-world applications, these graphing algorithms can be applied in a variety of ways, such as network trafficking, engineering, intelligent transportation systems, digital mapping, IP mapping, social networking, and and just to give an example of how it would work in one of these applications, social networking would imply that, you have your account and you have friends who have accounts, and the connections based on you having these friends are sort of feed into the algorithm being able to find suggestions for you to connect with other people based on the accounts that they have. Just an example of that, how that would work. So looking at the issue, currently serial shortest path algorithms have reached a time limitation. At this point, we can only achieve so much speed up trying to optimize a serial approach. The solution to this would be parallelization, through taking the serial code, which executes on a single CPU, and parallelizing it to run on multiple CPUs. Our goal is to improve the algorithms past the time limitations. This is achieved by the multiple CPUs running functions, which may be run several times concurrently. So if we look at the complexity of running these search algorithms in serial, or running Dijkstra's in serial specifically, we can see that the time complexity kind of goes up depending on how we are queuing nodes, or in this case with the graph, vertices and edges. So with an array, the memory would be the number of vertices, which is v, that we have in the array, and the time to execute that would be the amount of vertices squared. And then for an array from a lazy approach, the memory would be the number of edges, the time would be the number of vertices times the number of edges. For a sorted array, memory would be the number of vertices, time would be the number of vertices times the number of edges. For a heap, it would, as the same as the array and the sorted array, it would be the number of vertices. And a heap is a bit quicker, less complex time than using an array implementation. So we could get a little bit of an increase in speed with with the time complexity being the number of edges times the logarithm of the vertices. In a lazy approach with the heap, we would get the same sort of time complexity, and then with the Fibonacci heap, we would get a little bit worse of a time complexity. Or actually, no, this would be better, since we would have the edges plus the vertices times the logarithm of the vertices. So now we're going to break down Dijkstra's algorithm. Dijkstra's algorithm finds the length of the shortest path between two vertices in a graph. The algorithm works as follows. In the first step, we're going to choose a source vertex. In the second step, we define a set of vertices and initialize it to be an empty array or an empty set. So this would be an array or a heap, like we just discussed. As the algorithm progresses, the set will store those vertices to which a shortest path has been found. In step 3, we're going to label the source index with 0 and insert it into the set. In step 4, we consider all of the neighbors of the source or whichever node we're on. So we consider each vertex not in the set connected by an edge from the newly inserted vertex. We label the vertex not in the set with the label of the newly inserted vertex and the length of the edge. If the vertex is not in the set and was already labeled, its new label will be the minimum between the old label and the label that was just inserted plus the length of its edge. In step 5, we pick a vertex not in the set with the smallest label and we add it to the set. And then we repeat that until we reach the destination vertex, or until there are no more vertices to add. So if we walk through an example of that, here we have this graph with all of these vertices and these edges with their edge values. So if we pick 0 to be the source, we're going to go here. Now 0 is in the set. We're going to look at the vertices that are connected to it by the edge. And so the distance to this vertice has an edge weight of 2. The distance to this vertice has an edge weight of 9. Between the two of them, 2 is the shortest. So we're going to add 2 to the set. Or this vertice with a distance 2 away from it is the shortest, so we're going to add it to the set. So here we're going to look at all the nodes connected to this vertice, and that's going to be this vertice and this vertice. The edge weight to here is 1, so the distance from the source to this vertice would be 3. The edge weight from here to this one is 3, so the distance from the source to this vertice is going to be 5. Between the two of them, the distance that is 3 is shorter. And keep in mind, as we are looking at each vertice that is connected to the vertice we have just inserted, we're adding the distance to get to that vertice. So right here, we look at this vertice and this vertice. We see that here, that has a total distance of 3. This has a total distance of 5. Now, after we insert this vertice into the set, we're going to look at the ones that it's connected to by an edge, which is this vertice, which has an edge weight of 6, and this vertice, which has an edge weight of 1. Previously, this vertice, the minimum distance that we could find that vertice was 5, going through this vertice onto this one. Going through this most recent vertice that we added with an edge weight of 1, we can see that the minimum distance from the source to this vertice is 4, so we would update that. If we look at this one, we see that it's 9. 4 is the minimum between those two, so we add that to the set. And then 4, we're going to look at this vertice, which has a max distance from the source of 13, this vertice, which has a new updated distance from the source of 6, which is smaller than 9, so this vertice was updated with its minimum distance 6. And we're going to add this to the set, since 6 is less than 13. Once we add 6 to the set, we're going to look at its vertice. It only has one connected vertice, which will be 10. Or, no, excuse me, I misspoke. We're going to look at this, which is going to be 10, and then we're going to look at this vertice up here, which we can see is less than 10, since the total distance to get from the source to this vertice is only 9. So we add this one to the set. now that we have added this one to the set, we're going to look at its vertice, which can only go here. It has an edge weight to this vertice of 5, which would make the total distance from the source to this vertice 14. And then we're going to go back to here and look at its vertice, which is has a distance to this vertex, its next neighbor, of 4, and so from the source to this vertex is 10. This is the minimum between this vertex and this vertex, since this is 10 and that's 14. So we're going to add this one to the set. Now that this one's added to the set, we're going to look at its neighbors, which is going to be this vertex and this vertex, the two ones that have not been inserted yet. And from the source to this vertex is going to be 11, since this has an edge weight of 1. The source from here to there we already know is 14, but going through here we can take the shorter path. No, sorry, that's in the next step. So we know that this is going to be the shortest path because from here to there is going to end up being 15, which is greater than 14. So we're going to take this path to this vertex, which has a distance of 11. We're going to add this one to the set. Once that's added to the set, we're going to look at the only vertex that's left, which is here. And with this edge weight of 1, we can reduce the minimum cost to get to that node from 14 to 12, since the distance from the source to this node, to this vertex would only be 12. So using this, Dijkstra's algorithm has allowed us to find the minimum cost to get from the source vertex to the end vertex while visiting every vertex in the graph. And there would be a little bit of extra work to tweak the algorithm to get back the shortest path, but using this we can backtrack and find the shortest path using these edge values.
So the serial version of Dijkstra's algorithm that was used in this research paper used two sets of nodes. The first was D for discovered, and the second was U for undiscovered. At first, only the source node was placed in D, and the distance from a node to each of its non-neighbors is set to infinity. Then the node in set U with the minimum distance to the source node would be added to set D, and the new minimum distance from the source to each of this node's undiscovered neighbors would be found, and then the process would be repeated until all of the nodes are in D and set U is empty, and that would find the shortest path from the source to every node. For the parallel version of Dijkstra's, there are two different strategies we can use. The first strategy, you execute n different shortest path problems on different processors. And in the second strategy, you actually parallelize the Dijkstra's algorithm itself and try to run what you can from it concurrently. And this uses n different processors to find the shortest path from a vertex to all the other vertices using the sequential Dijkstra's algorithm. It uses OpenMp, which is open multiprocessing, and that's a loop-level parallelism ATI that's available on C, C++, and Fortran, and it identifies regions that are able to be paralleled and then executes them in parallel. So it'll start with one master thread, and then when it comes to a place where it can parallelize what's happening, the master thread will create a team of threads and execute the parallel regions. And this is primarily pragma-based, so it's really easy to switch between and combine serial and parallel code. Specifically in this parallel implementation of Dijkstra's algorithm, we start by creating a graph data structure that has the vertices and edges that connect the vertices. This is represented by a 2D array of edge weights, and these weights represent the cost of travel between a node. So if two nodes you can't reach each other or are not neighbors, then that distance will be infinite, and if they are neighbors, then it will be the weight between them. And the execution of this algorithm will return an array of size n, where n is the number of vertices, and that array will store the shortest distance from the source vertex to every other vertex. There are two phases in this parallelization algorithm. The first phase is going to visit all of the nodes that have been marked and determine the cost to visit all of its neighbors. And if the cost on that node plus the new edge weight is less than what it currently is for that neighbor, then it'll be replaced with the shortest one. And the second phase is going to check to see if there's a smaller cost that's been discovered for a vertex, and it's going to mark those as being needed to visit and update the cost array. Both of these phases are necessary because synchronization isn't really possible for local groups in OpenCL. It's going to use partitioning to split the workload between available hardware, which can be the CPU or GPU, and each kernel processes one vertex.
All right, now we're going to talk about the experiment and results and analysis part of the research paper. In this, there were 4 different configurations. In this section, there were 4 different configurations used. All configurations had a type of dual processor. There were 4 unique processors used in these experiments, or at least for the first experiment. There were 3 unique CPUs used in these experiments, and the execution speed for each of the 3 algorithms mentioned before were all tested on these processors and these configurations. So the three mentioned before were the sequential Dijkstra's algorithm, the parallel Dijkstra's algorithm, and the OpenCL Dijkstra's algorithm. Real quick, I want to go through the configurations and show and just mention what they used, so that way you guys have some sort of context to these different graphs that I'm about to show you in a second. So configuration 1 was the Intel i5 CPU clocked at 2.5 gigahertz. This is the fastest of all the configurations in terms of clock speed and processing power. It is this particular CPU is a 2-core 4-thread CPU. The GPU used for this configuration was the AMD HD 6500M, or the 5706, or the 5600, or the 5700 series. This is what they mentioned in there. I don't know that they knew what the GPU in this processor was, and that was just the name of the graphics driver that they found, which is unfortunate. This is a little bit of ambiguity in there. Configuration 2, however, used the Intel Pentium dual-core CPU, clocked at 1.6 gigahertz, and it also used an Intel GMA X3100 as the GPU. This is a standard GPU used in a lot of older laptops. The Intel Clarion dual-core CPU was used in configuration 3. It was also clocked at 1.6 or 1.86 gigahertz, and this configuration has the same GPU as the previous one, as the Intel GMA X3100. Like I said, a standard for older laptops. And then finally we're on to the last configuration, which is the Intel Core Duo, which is clocked at 1.8 gigahertz. This is also a dual-core processor with at least and it has 4 threads. It is the slowest clock speed of all of them, and the GPU used in this one is a mobile Intel 965. That is a very hard GPU to find information on online, so I do not know a lot about that GPU, but good news is it was never used later in this report. So we're going to talk about the experiment 1 now. There were 2 experiments used in this paper, and this is the first one. This is the parallel versus sequential execution time, which, as you can probably guess, the goal is to determine the relationship between the parallel Dijkstra's algorithm execution time and the sequential Dijkstra's algorithm execution time. For this, the sequential algorithm was ran on all 4 of the configurations, and compared to that of the OpenCL parallel Dijkstra's algorithm, ran on all 4 different configurations as well. And we're going to talk about their results. So, as seen earlier, configuration 1 had the highest clock speed of any of the configurations, and probably the best processor of any of the configurations, and it shows that around 2,000 nodes there starts to become speed up between the parallel and the execution, and the parallel becomes faster than the serial execution time. In configuration 2, that same speed up isn't seen until around 3,000 nodes in the graph. And configuration 2 was the configuration with the Pentium CPU from Intel. In configuration 3, the speed up also isn't seen until about 3,000 nodes in the graph. And configuration 3 was the one with the Clarion CPU. And also in configuration 3, you can see towards the top of the graph is that it starts to become slower, or the speed up is not as great as before and earlier in the graph, or say around 4,000 nodes between the serial and parallel executions. And finally, configuration 4, which was the slowest of the 4, also doesn't start to see speed ups until, say, 2,500 nodes, or even later, where it becomes more obvious as 3,000 nodes. The parallel execution times for that seem to speed up faster than they do with the previous 2 configurations. So the results from experiment 1, we can see that configuration 1 was the best performer by far, and configuration 1 was the one with the i5 clocked at 2.5 gigahertz with the AMD graphics card, the 3 different graphics card series. All configurations, however, did see execution times with the parallel Dijkstra algorithm versus sequential algorithms. They saw faster execution times when the number of nodes exceeded 3,000. For most of them, though, however, they did not see substantial speed up before the nodes exceeded 3,000, with the exception of configuration 1. So from that, they took configuration 1. They decided that since it was the best performer, they were going to perform experiment 2 on it. And in experiment 2, they compare the execution time of the algorithm, of the parallel algorithm on configuration 1 with different edges per node. And the goal of this experiment was to determine if the amount of edges per node has an effect on the processor and GPU execution times, and which one of those 2 would be faster between the the two execution, or which one of those would be faster to execute the parallel Dijkstra's algorithm. In this, there were 4 cases used. There were 5 edges per node, 10 edges per node, 20 edges per node, and finally 50 edges per node were used as the 4 different cases in this, and they were all run on configuration 1. And now you can see from these graphs is that with 5 edges per node, the GPU execution times are pretty much faster than the CPU execution time across the board. On 10 edges per node, it becomes a little bit more ambiguous in that, well, the CPU is mostly slower, but also it's, aside from a large gap around 40,000 nodes or 50,000 nodes in the graph, there are, for the most part, the same, and that also could have had an effect for some reason on, as you can see coming up in the next one, on 20 edges per node, they're almost identical. The CPU and GPU execution times have not hardly deviated at all, and when we go up to 50 edges per node, they are both atrociously slow, and they both pretty much execute the same way every single time. So finally, the experiment 2 results, as mentioned before, is the number of edges per node affect the overall performance on both the GPU and the CPU. I mean, that was pretty much expected. The performance of the GPU are better than the performance on the GPU is better than that on the CPU when the edges per nodes are less than 10. When the number of edges per node become more than 10, there is no significant performance differences that can be determined. This is probably due to limitations with the GPU and the CPU more than it is. These numbers could change, say, if you had a more powerful CPU and GPU. This means that for the speed up ratio of the parallel algorithm are basically unchanged between the performance of the CPU and the GPU.
So moving on to the conclusion. So in conclusion, parallel programming is a growing and important field in computer science, not one that will be going away anytime soon. Probably one that we will just keep working more with and needing to expand into. And some algorithms may just be difficult to parallelize in a multi-threaded way, which an example of these may be Dijkstra's specifically. Some major issues with it are the limited explicit parallelism and the excessive need for synchronization, especially in an implementation such as the one used, relying on a priority queue, since that hurts the parallel potential. In evaluating a vertex at the head of the priority queue may change the order of the elements remaining in the queue, which is not necessarily a correct or efficient way to run an algorithm, and also can lead to the parallel ending up doing more work even though it may do the work faster still. So their final conclusion was they achieved an average speedup ratio of 10%. So what is speedup? Speedup is somewhat subjective of a number. 10% speedup could be significant for some cases and not in others, but 10% speedup is not necessarily a great number for just any parallelization, or specifically this case. However, at a larger node or larger runtime, it may make a big difference. So the speedup is found through Amdahl's law, and it is basically the S latency is the speedup, and the S is the percent speeding up, and P is the percent time better than the previous time. So in cases of a larger number of graph nodes, the speedup could potentially be significant or necessary. However, many practical cases of routing would not deal with the 2,000 to 3,000 node range, which is necessary for the serial to become noticeably slower than the parallel version in their testings. However, in a case like a social network where you have like Twitter, Facebook, LinkedIn, Instagram trying to connect thousands of people and suggest followers based on the people acting as nodes, this would probably be significant and may be necessary to help the algorithms run faster. So some reasons for our findings. Number one is inefficient code. and code that could be optimized or set up more efficiently, especially when it comes to memory access times and stuff like that. Another reason could be that for small amounts of nodes, more time could be spent on parallelizing and synchronization than is spent on the sequential code, which basically would result in the priority queue or the cost checking, leading to more calculations for the parallelized version than they would actually even end up running for the serial version in smaller node counts. So for further work, they highlighted utilizing shared memory, avoiding branches, selection of appropriate data structures for the algorithm, and designing algorithms correctly, which would somewhat go together hand in hand. And then also they highlighted that they could be potentially more significant on better processors, since the processors used in this research paper were not top of the line gear and were somewhat slower processors for today's standards. So some final thoughts. Some problems discovered here may be just inherent to Dijkstra's algorithm. The algorithm was designed to be sequential and may not lend itself fully into parallelization, as some algorithms do not parallelize very well. And we could also be reaching the point of diminishing returns, which is basically that the development time may not be worth the speed up gained in this algorithm, and that's shown in the next slides here where we kind of bring it back to the graphs. So diminishing returns is basically the point where your results kind of plateau based on the energy that you're spending to achieve them. And that can be seen here for the edges per node performance, where you can kind of see both of these end up plateauing at a certain point where it doesn't necessarily matter too much how much you're doing. And that can be shown here as well. And so in conclusion, Dijkstra's algorithm just may not parallelize fully well and may be better as a serial algorithm, though some speedups were found and can be achieved, especially at higher numbers of nodes. Thank you all for your time. I hope you enjoyed the presentation.